Welcome back, everyone. I mean, the exercise was a little bit dense, and I noticed this in the breakout rooms. But overall, many of you did very, very well. And actually, some of you completed it to the end, which is great. I will briefly try to solve it in a very short time, and relying on what we have achieved so far in our learning of MATLAB syntax. So let's actually try to see what is needed. First of all, I need to define some sort of a true value for the cosine of x. That's based on the MATLAB built-in cosine function. That's the true value of cosine x. MATLAB can calculate it for us. Then I need to start loop. You know, there's a while loop and there is an end. And I need to end as long as certain error is, certain error is greater than the acceptable error from the user. So, for example, I can call it the true error because I want true error as long as the true error is greater than the acceptable error, acceptable underscore error. Then, as long as this is the case, you should keep looping. But then there is a problem here. I haven't calculated the true error yet, right? Then this loop, MATLAB is gonna reject it automatically because I didn't define what is a true error yet, right? All what I have is the true value, but I can calculate at least the true error for the first term, right? I can say, for example, that, estimated, let's call it this, estimated cosine. If I take the first term only, the estimated value of the cosine is going to be 1. I can calculate my first error based on this one. So I can calculate true error.
Share screen.
Oh, am I not sharing? I'm sorry for this. Thank you. Thank you for pointing this out. Very, very sorry, guys. That's what I wrote. I basically wrote true value equal cosine x. And then I made a while loop that stopped based on the true error. So as long as the true error is greater than the acceptable error, it's gonna keep looping. But then I faced an issue. I don't have a value for the true error. So I decided to do the first term in the loop separately. In the Taylor series separately before the loop. So I'm gonna calculate true error equal my estimated cosine, right, minus the true value of the cosine, right? And here you have to really build the brackets very, very carefully, as we learned it before. This is divided by the true value, and then the whole thing, you take its absolute value and make it a percentage. You need to multiply by 100. Maybe you can do this 100 multiplication at the beginning. Okay. So that's the true error. But one more thing, I need to store these errors into an array. I just don't want one value for the error. I want the error after 1 term, the error after 2 terms, the error after 3 terms, the error after 4 terms. So because of this, I'm gonna call this true error of 1. That's the first element in the array true error. Then inside the loop, I will calculate true error of 2, true error of 3, true error of 4, true error of 5, and store them. To help me doing this, I'm gonna use a counter. Let's call it 1. It starts as 1. And inside the array, this counter will increase 1 at a time. So it's going to be 2, 3, 4, 5, 6, 7, and so on and so forth. Okay. So because of this, the while loop is not going to be based on true error. It's going to be true error of A. So I need to compare the true error after the first term. Is it greater than the acceptable error or not? If it is greater, then I will continue. Suppose I finished and calculated 2 terms, then I will check. is the true error of 2 greater than the acceptable error or not? If it is greater, then I go to the third term and then calculate true error of 3 and so on and so forth. That's basically how I do it, okay? So incremented k equal k plus 1, but I need to calculate the new estimate or the estimated cosine here. So I need basically to take one more term, which is x squared over 2. And next time I will take x4 over 4, over factorial 4. So how do I do this? Well, my estimated cosine, let me copy this variable, my estimated cosine equals the previous estimated cosine plus what? Plus, let me code this, x power, let's code it together. So let's test, for example, x power k divided by factorial k, okay? Or actually, since it's appearing in in even numbers like x squared, x4, x6, x8, maybe I should try, 2 times k here, factorial 2 times k as well. Let's see if this works. Apparently, it's not going to work, and we will see why. So I started with k equal 1. I enter inside the loop. The k is going to be 2. So the value of k now is 2. So when I go here and try to calculate, my estimated cosine is going to be the previous value of estimated cosine, which is 1, plus, so let's put here, x 2 times k. So k is 2, and I multiply it by 2, so it's going to be 4, divided by factorial 4. That's a problem, because I missed a term, right? I missed the term, which is x squared minus over factorial 2, right? And someone might suggest removing the 2, but that doesn't work. So one of you might suggest, hey, just remove this 2 and you will be fine. No, I will not be fine, because when k equals 3, I will be calculating x3 over factorial 3, and that does not exist in the series. The only way to fix this, or one way to fix this, I shouldn't say the only, but one way to fix this is to replace k with k minus 1. Same thing here. I replace k with k minus 1. Why is this? Why this is gonna work? Well, let's try to think about it. Let's follow the loop. If I start with k equal 1, first time an increment, the k is gonna be 2. And then when I calculate this expression, it's gonna be the previous estimated cosine, which is 1, plus x, k minus 1 is 1. 1 times 2, so that gives me x squared, divided by factorial. K minus 1 is 1, times 2 is 2, so that gives me factorial 2. Next time when I iterate, the value of k is gonna be 3. Estimated cosine will have the value of 1 plus x squared over factorial 2, right? Sorry, there's no factorial here. And then when I calculate this, k is 3. 3 minus 1 is 2. 2 times 2 is 4. So that's going to give me x power 4. Divided by, k is 3. K minus 1 is 2. 2 times 2 is 4. So it's going to be x4 over factorial 4. So I am progressing in the right direction. So this way, with the trick of putting k minus 1, I am progressing in the right direction. So that's my estimated cosine. After I calculate my estimated cosine, I need to calculate the true error one more time. So I'm going to copy this. Paste it here. So this is not true error of 1. This is true error of k, because I'm storing it in the memory of the computer. And you can keep track of the number of terms that you have been using. There are many ways to do this, but I'm just using a very naive way. That number of terms of k equals k. So when k equal 2, the number of terms of 2 is going to be 2. When k equal 3, the number of terms of 3 is going to be equal 3. So it's just it records how many terms did we use. But we forgot to put at the beginning that number of terms of 1 equals 1. Now I'm ready to plot. So, and I was asked to use log log. So log log. I'm plotting the number of terms versus the true error. You can label the axes. X label is the number of terms. You know, Y label is gonna be percent true error. And if you want a legend, that legend is the error, or the percent true error. If you want, that's a legend. Let's try to save this and to apply this function. Let's copy this and go to the command window, clear all, TLT, paste it. Look, let's try the case x equal 1, an acceptable error. So how do you write 10 to the power minus 13? So some of you write it this way, 10 raised to power minus 13. But there is actually an easier way. You can type 1e minus 13. 1e minus 13. That's basically 1 times 10 to the power minus 13. That's a nice syntax to remember. Let's try this. Guys, do you see the plot here? Maybe I should stop sharing and reshare. Do you see the plot here? That's the output. So after one term, the error was something like, 90-something%. After 2 terms, the error is 2.79%. 3 terms, the error is 0.09%, and so on and so forth. And after 9 terms, the error became less than 10 to the minus 13, right? You can test this with another case. So let's do CLC and clear all. Let's test it with another case, maybe with Shine 7. Let's see how it works. So do coshine 7 took us more terms. It needed more terms. So I think it needed up like to 11 terms or some, 18 terms. It went to 18 terms to calculate coshine 7 with such an accuracy, right? I'm gonna stop here because we are a bit over time. And if there are questions on the chat or the shadow meeting, I'm happy to address them. Or you can unmute yourself and ask right away. This is a kind of elaborate exercise. We have done while loops. We did some plotting. We kept a track of arrays. How do they increase? Any question? Okay. Okay, so that was a big exercise. Please, if anyone in this room or is in the shadow room is still, missing something, please go over the recording one more time and try yourself. If there is an issue, we can cover it next time. So next time we are planning to have, some miscellaneous topics ranging from arrays, digging deeper a little bit in arrays, using MATLAB for matrix calculations, simple matrix calculation. Go over some of the useful built-in functions, some of them, okay, there are tons of them, and you can just use whatever you want. And, it's gonna be a set of miscellaneous topics that we will cover next time. Thank you so much, guys, and I'll talk to all of you soon. See you later. Bye.